Hello and welcome to lecture 35 of the course Computational Complexity. In the previous lecture, we saw circuits, many examples of circuits, many different constructions of the same function, many different constructions for the same function, right? The threshold 2 function. So hopefully we have an idea of what really is a circuit, right? So, but now we'll see the formal definition and some associated other definitions, right? So, as I had indicated in the previous lecture, a circuit is nothing but a directed acyclic graph, and that have n designated inputs, right, and a single output. So, that if you see it as a DAG or a directed acyclic graph, the n inputs are source vertices, meaning all the edges are outgoing edges, and the output is a sink vertex, meaning there are only incoming edges, right, edges or edge, right, and all the edges or all the vertices that are not the input vertices are gates, right, and these gates are from a basis, meaning these gates, in all the examples that we saw, we allowed only AND gates and OR gates and NOT gates, but perhaps you could allow, let's say, XOR gates, right? Perhaps you could allow some other strange function, maybe threshold gates, right? Okay, but most of what we do will be only on the AND gate, OR gate, and NOT gate. But in general, a circuit could be formed out of other bases, right? So, but for the rest of this lecture and for the subsequent lectures, we'll assume that we have AND gate, OR gate, and NOT gate, right? And usually it will be bounded fan in 2 or something, but we will make it clear when we have gates that have unbounded fan. Okay, so again, usually we will have a De Morgan basis. So the word De Morgan basis stands for AND gates, OR gates, and NOT gate with fan in, and where AND and OR have fan in 2. Okay, De Morgan basis. And one thing to note is that, again, given a circuit, it computes a Boolean function from 0, 1 to the n to 0, 1, right? So it's a Boolean function, and so all that we will be doing in this course is computing functions with only one output. So you could, in theory, compute a function, like, meaning from an n bit input you compute an m bit output. That's also possible, but what we will be doing in this course is only, we will only look at 1 bit outputs, right? That itself is quite rich and captures a lot of interesting ideas, right? And typically that goes along the lines of what we have been doing so far. So far we have been mostly dealing with decision problems, right? Given is this formula satisfiable, is this graph 3 colorable, right, is this number prime, right? So mostly we have been dealing with decision problems, not compute a function of a given input, right? So now one thing to note is that it takes an n bit input and produces 1 bit output. But now it's not very clear, or not very immediately clear, how this can be used for a computation, right? Let's say you want to solve a SAT instance, right? A Turing machine is, you just give it the input and it does whatever processing it does, and then decides accept, reject, and so on, right? But a certain fixed circuit, right? Let's say I have a circuit that has n bits, now n bit input, right? Now this will take only inputs of a certain size, the n bit size, right? But given a fixed circuit, it cannot possibly compute SAT instances of all sizes, right? So now how do we formalize the notion of computing a language using a circuit, right? So be it SAT, be it 3 colorable, be it shortest path, whatever, how can we use circuits to compute a decision, a language which have all inputs of all sizes, right? So what we will do is to use a family of circuits, right? We will have a family of circuits, one for each input size, right? And each circuit of the corresponding input size is supposed to handle that input size, right? So what we will have is a family of circuits. So we'll use script C to denote a family of circuits C sub I. So Ci is a circuit that takes I bits as input and outputs a single bit, right? And we say that this decides a language A, the family decides a language A, if the ith circuit in the family decides A correctly for all the I bit instances of A, right? So if the language corresponding to the, so I have used n here, okay, maybe I'll replace it with I. The language corresponding to the ICI is nothing but all the I bit instances of A. Okay, so the language corresponding to Ci, and what is the language corresponding to Ci? Language corresponding to Ci is those sets of inputs, those sets of I bit inputs, right? Remember, Ci only takes as input I bit strings. Those I bit strings for which Ci evaluates to 1. So given any I bit input, any input, there are some inputs which evaluate to 1, some which evaluate to 0. So Cix denotes those inputs that evaluate to 1, or sorry, Cix is just the evaluation. The language corresponding to Ci denotes those strings for which Ci evaluates to 1, right? So where Ci is just the evaluation of Ci on the input x. And we say that a language A, right, is in the size Sn if there is a family of family of circuits of size Sn that decides A, right? So just once more, so suppose A is a big language, right, and right, so all 0 bit instances, 1 bit instances, so this is A, right? So you can slice A into 0 bit instances, 1 bit instances, all of them in A, right? And we want, so the ith slice, right, this is the ith slice of A, which means it's the set of strings in A that are of length exactly I, that are in A. Now we want the circuit Ci to accept exactly, or to evaluate on to 1 to exactly these inputs, that of length I, right, that are in A, right? So that is the requirement. So you can think of the circuit family looking at each slice, right? And we say that A belongs to size of Sn, right, if there is a family of circuits of size Sn that decides A. So when do I say that? So now what do I mean by saying, when I say that a family C of size Sn? What I mean is that the family is C1, C2, C3, it's a family of circuits. So I want C1 to be at most of size at most S of 1, C2 to be of size at most S of 2, C3 to be of size at most S of 3, and so on. So I want Ci to be of size at most S of I for all I, right? This is when I say C is a family of size Sn. So basically for any I, the size of Ci should be at most Si, right? So so hope this is clear. And one thing to note is that is this important distinction between circuits and Turing machines, which you may have noticed already. Turing machine that does something, let's say palindrome, right, or decides the shortest path, whether right, or it just, there is a certain algorithm that it encodes, right, and it will take all inputs of all sizes, right? So if we have to run a Turing machine that tests palindrome, you could give it any length input and it will take care of it. Whereas circuits, it needs a specific circuit for each input size. So now this this is what is called non-uniformity, right? So potentially each input size could be handled differently because we need different circuits for each input size. And now I could have a certain structure for a certain like I equal to 10, and a different structure for I equal to 11, and yet another different structure for I equal to 12, right? This is not really something that happens in Turing machines. So this particular feature is called non-uniformity, right? And we will see how this plays an important role in the upcoming lectures, right? So this non-uniform way of computing is something that circuits have. There are also other models that have this property, but this is something that circuits have. And this sometimes, if it is not restricted properly, it gives a lot of power to the circuits. So let's see, we will see that in the upcoming lectures, right? So coming back to family of size Sn, family of size Sn is where each Ci is of size Si, right? And similarly, we could define other measures like number of wires and depth. Again, depth is you can view the circuit as a tree, right, or a directed acyclic graph, right? So what is the maximum length of it? So the output will be at the top, right, the red one, and let's say the green ones are the inputs. So what is the length of the longest path from an input to the output? That is the depth. So if you look at it as a tree, then it is just the height of the tree or depth of the tree, right? So what is the longest path from the red to any green, right? So you could also define depth, a family of circuits that have some dn depth in a similar manner. And another point is that I haven't explicitly said, but we will only from now on we will only be focusing on Boolean functions and Boolean circuits. Boolean functions means 0 1 to the n going to 0 1, right? You could have arithmetic circuits that deal with numbers over a field and so on, but we will not be looking at that, at least in the next few lectures. Okay. Now, a couple of more definitions that I just want to state now. We won't be immediately using them, but a couple of more definitions. These are very important definitions, both in terms of circuits as well as functions. So, symmetric functions are those functions when that again everything is Boolean from now on, right? It takes a bunch of input bits and produces a 0 1 output. A symmetric function is a function whose value is unchanged when you permute the input bits. So if f is a symmetric function, then f of x1, x2, x3 will be the same as f of x2, x1, x3. It doesn't matter how you permute it. It's the same as f of x3, x2, x1, right? So any way you permute it, it's the same. All 6 ways will be the same. So many functions that we can think of are symmetric. So AND is a symmetric function, right? It doesn't matter in what order you give the inputs. OR is a symmetric function. XOR is also a symmetric function. Unless you have some function like negation of x and y, right? So that will not be symmetric. So examples are AND, OR, etc. Right? So you need this is defined only for functions of multiple inputs, right? So if you have like single bit input, then this becomes a kind of a not very meaningful definition, right? The next definition is monotone function. A monotone function is a function where if x is less than or equal to y, then f of x will be less than or equal to y, f of y. Right. So in terms of like in the regime that we are in, we are talking about n bit vectors as inputs and 0 1 as output, right? So when I say x is less than or equal to y, what I mean is in a bitwise manner. So you can look at it each bit by bit, x should be less than or equal to y. So there should not be a position k where x is 1 and y is 0. everything else is okay. X could be 0, y could be 0, x could be 1, y could be 1, and x could be 0, y could be 1. But x less than or equal to y means there could not be any bit position where x is 1 and y should be 0. So if x is less than or equal to y, then f of x is less than or equal to f of y. And monotone, being monotone is a rather natural property, right? So for instance, given a graph, does it have a clique of size 10, right? And suppose the graph is expressed as a string of edges. So you have, let's say the graph can have, let's say graph has 20 vertices or 100 vertices, then it has 100 choose to edges. So it's expressed as a string of edges. Now you are asking if the graph has a clique of size 10. So now if I add an edge, right, then if the original graph had a clique of size 10, the addition of an edge will still continue to have that clique. However, if you did not have a clique of size 10, then the addition could potentially create a clique of size 10, but it need not create. But if you add an edge, one thing is for sure, it will not remove a clique that is already there. So this is a monotone property. So many natural properties, especially in the context of graphs, are monotone functions. Right. So a function that takes a graph as input and denotes whether it has a clique of a certain size is a monotone function. Right. Or a matching of a certain size, that will also be a monotone function. So even AND is a monotone function, just because, so, right, and OR is also a monotone function. If you flip an input from 0 to 1, then the output can possibly flip from 0 to 1, but it cannot flip from 1 to 0. Right. And another function, another definition is of monotone circuits. Monotone circuits are those circuits that use only and OR gates. Right. So you can only have two types of gates, AND or OR. And one thing that is interesting, extremely interesting, is that it's not a coincidence that monotone functions and monotone circuits have the same name. This is because monotone functions rather function f maybe I just write this even though it really doesn't, is a monotone function if and only if it has a monotone circuits representation. So the set of all functions that can be expressed using monotone circuits are exactly the class of monotone functions. So that's why I said the naming is not an accident. So this is something that you can try to show. It's maybe it may require a bit of thought, but it's something that you can try. Right. Now this one important theorem, it is that given any language, right, this language has a circuit family of size of exponential size, exponential meaning order 2 power n size for any language. Right? So this is something that is interesting and something that we do not have in the case of Turing machines. It's not like we cannot say that any language has a 2 power n time algorithm. There are languages that require more time, right? So let's see how that is. It's a fairly straightforward argument. So consider a function, right? So first of all, when I say language, we can, as I said already, we can restrict it into strips of a certain size, right? So so consider any function, right? Let f correspond to the to the strip of L of input size. Okay, so now, so f is an arbitrary function that corresponds to the, so L is an arbitrary language, so f is an arbitrary function, right? So f corresponds to the strip of n length n. So set of all f will be 1 only exactly on those inputs where which are in L and of length n, right? So f is an n bit function on n bits. Now consider that. So now all we will do is that we will just show that f has a order 2 power n sized circuit representation, and that is enough, right? Right. So we will show that f has a order 2 power n sized circuit representation. So now let us see how f can be written. So we could decompose f like this. So we could consider f where x1 is set to 1 and f where x1 is set to 0, right? x1 is set to 1 and x1 is set to 0, and you take the AND of the first with x1 and the second term with x1 complement, right? That is the AND of the first term with x1 and second term with x1 complement. So when x, and then the OR of these two factors, right? So when x1 is equal to 1, the first term is only the first term comes into play, because the second one becomes negation of x1 is 0, so it just vanishes, and we have f of 1 comma x2 etc. And similarly when x1 is 0, only the second term comes to play, so again it is fine. So you can easily verify that this equation is valid. Now all that we are going to do is to just build on this equation and rely on an inductive argument for the, or inductive or recurrence relation based argument for deriving the size of f, right? So f is x1 and f of 1, x2 and so on, or x1 complement and f of 0 and so on. So now suppose we have two boxes or two black boxes. The red black box computes f of 0, x2 etc. up to xn, and the green black box computes f of 1, x2 up to xn. And but then these needs the input x2 up to xn. They don't need x1, but they need the rest of the input bits, right? So we give that, and then you can easily verify that this computes exactly what we have here. You take an AND of f of the red box with x1 complement and the green box with the output of the green box with x1, and then have an OR, and that's it. So this is a circuit that corresponds to this function f, right? So you can verify that this is a circuit that corresponds to the above expression. Now so suppose Sn is the size required to construct a function of a certain an arbitrary function of from 0 1 to n to 0 1, right? So f requires an Sn size circuit, and inductively speaking, we are relying on two Sn minus 1 size circuits, right? Because once we hard code 0 or 1, the rest of it is actually a function on n bits, n minus 1 bits, right? So the green box and red box are both actually functions on n minus 1 bits, right? Because one bit is fixed and you could simplify whatever. And so there are two, so let us say Sn minus 1 is the bound, size bound for any function that requires n minus 1 bits. Similarly, Sn is the size bound for any function that requires n bits, right? So Sn is actually, so size of n is actually, if you use this construction, it is 2 times Sn minus 1, one for the red box and one for the green box. And then how many other gates are there? So size is the total number of gates. So number of gates in the red box, number of gates in the green box, and then there are 4 other gates. So plus 4, right? And what is the base case? The base case is S of 1 equal to 1. when you have a 1-bit input and output, basically you just you have at most a single wire, x1 equal to x1, x1 equal to 0, x1 equal to 1. There are only 4 possible functions, or x1 equal, the function is the complement of input. But in each of these cases, the number of gates required is at most 1. So S of 1 equal to 1. And if you solve this recurrence relation, you will get this expression. Sn is 5 divided by 2 multiplied by 2 power n minus 4. And this is order 2 power n. And that's it. So this shows that any function can be constructed in order 2 power n size. To be more particular, to be more precise, it's 5 divided by 2 times 2 power n. So it's an inductive argument because a recursive argument. Right. In fact, this is a very simple idea, but if you look a bit more closer and study it a bit more, using a bit slightly more involved ideas, you could show that actually for any language L, you have a 2 power n divided by n size circuit. So here we show that it's order 2 power n size circuit. So now I am saying that actually this order 2 power n can be reduced to 2 power n divided by n, and this theorem is due to Lupanov. Yeah. So in fact there is a tighter bound available, and the 2 power n divided by n bound is actually, this is somewhat tight. You cannot make it, you cannot really improve it, in the sense that you can probably improve the constant, but nothing beyond that. So that's what I mean by somewhat tight. So any function has a circuit of order 2 power n divided by n size, and what we saw was any function has a circuit of size order 2 power n, any function or language. And with that I will close this lecture. So we saw the definition of a circuit. We saw what one means when we say that a circuit can compute a language, right? So by dividing this language into strips of each size, we saw, so this is basically the idea of non-uniformity, right? And we also saw when so we need a family of circuits to decide a certain language. So we saw the definition of what we mean when we say the family has a certain size or a certain depth. And then we saw this theorem that said that any language has a order 2 power n size circuit, and we also stated that any language has a order 2 power n divided by n size circuit, but did not prove it. And with that I will close this lecture. Thank you.